Hello and welcome. This video presents our ICCV 2025 work, STDDNet, a novel method that pioneers the use of Mamba for video polyp segmentation. We achieve this through two key innovations: spatial-aligned temporal modeling and discriminative dynamic representation learning. According to 2022 global cancer statistics from the International Agency for Research on Cancer, colorectal cancer ranks as the third most common cancer worldwide, yet it has the second highest mortality rate. This underscores the critical importance of colorectal health. Colorectal cancer typically begins with polyps, and early removal can prevent cancer. Colonoscopy is the primary detection tool, but its diagnostic performance is subjective, with polyp miss rate exceeding 25%. This is why we need automated polyp segmentation in video scans to improve accuracy. However, training a neural network to achieve the VPS task faces some challenges. First, the boundaries between polyps and their surroundings are ambiguous, as shown in examples A and B. Second, rapid camera movement causes significant variation in the scale, contrast, and position of close-up targets, shown in C2E. Third, to be clinically useful, the segmentation model must perform inference in real time. To overcome transformers' inefficiency, Mamba was proposed using selective state space models. Its vision adaptation, Vision Mamba, processes image patches with bidirectional scanning strategy for comprehensive feature extraction. This is overview of our STDDNet that leverages Vision Mamba both temporally and spatially to address the challenges of VPS. First, a pre-trained image backbone extracts multi-level features from the input clip. Then, compression layers are applied to compress the channels of these features. Subsequently, the STDP module models spatial-aligned temporal consistency between consecutive frames. To perceive fine-grained details in individual frames, the DDFE module extracts frame-wise dynamic information from low-level structural features with a gated dynamic activation unit. In the STDP module, input features are first horizontally concatenated, and a bidirectional Mamba block is applied on these features to model spatial-aligned temporal dependencies. Then, a filter uses initial predictions as a semantic guide to propagate the dependency related to foreground targets. The DDFE module first uses a Mamba block to extract structural features from the input features. Then, the GDAU operates on the structural and each frame features in a frame-wise manner to compute static value, varying value, and dynamic map. Finally, it activates the dynamic regions in each frame according to an activation ratio derived from current and previous masks, highlighting the inter-frame differences. In the Mamba block of DDFE, we utilize the reversed maps of the course prediction masks to complement relative position information. We evaluate our method on two public video polyp datasets. SunSeg dataset is a large-scale polyp video dataset with dense semantic annotations. CDC Clinic DB is a simpler polyp dataset. While it is not primarily designed as a polyp video dataset, its sequential frames offer short-term temporal information. We compare our method with other state-of-the-art approaches. The results demonstrate that our method outperforms other competitors in all metrics. The performance efficiency comparisons with other methods show that STDDNet achieves a better balance between accuracy and inference speed. We also provide a visual comparison with other methods, which clearly demonstrates the effectiveness of our segmentation model. In summary, we propose a novel and efficient network based on Vision Mamba for video polyp segmentation. Our model introduces two key modules, STDP and DDFE, to improve the colonoscopy video's understanding. For future work, we plan to develop a hierarchical recurrent yet lightweight spatiotemporal tracking and analysis mechanism. Thanks for your listening.